In this video, we're going to address concepts of what's known as conditional probability, and we're going to introduce it by means of an example. So we're going to suppose that we throw two fair dice, and we're going to define two events. Event A, which is that the first die comes up as a 3, and event B is that the sum of the two dice is a 6. And if we take a look over here, it's sort of a structure for the sample space. We don't need to fill in all the totals. We know that the outcomes, among the 36 outcomes, there are 6 that involve the first die being a 3, and they are these. And so I'll label those cells with an A, just to get us organized a little bit. And then event B is that the sum is a 6, and so I'll look at all the cells where the sum is a 6, and I'll enter a B in them. And you can see that there is one cell where they overlap, so the intersection of these two events is not empty. And we're just going to ask ourselves a bunch of questions about the associated probabilities. And we're going to start off easy with the probability of event A. That is just going to be the number of outcomes that involve event A, which is 6, divided by the total number of outcomes in the sample space, which is 36, and of course that fraction reduces. We could ask ourselves the probability of B, and that would be 5/36, because 5 of the 36 outcomes involve outcome B. We could then ask ourselves the probability of the intersection, the probability of both A and B, and that will be the number of outcomes involving both, which is 1, divided by the number of outcomes in the sample space, which is 36. We could ask about the probability of a union B, A or B. That would be all the outcomes that involve A or B or both, but everything counted only once, and so we've got these 6, 7, 8, 9, 10 altogether out of 36, which is 5/18 if we're reducing. But now we're going to ask a question of a kind we haven't asked before, and that is that assuming that B has occurred, what is the probability of A? And there's a notation for this. It's the usual P, and then A, since that's what we're asking about, and then a vertical bar, and then B, and that's read the probability of A given B, or A assuming that B has happened. And this assumption that we know event B has occurred is going to pretty severely restrict the outcomes that are under consideration, because if we know B has already happened, we no longer have 36 outcomes in play. We only have 5. And of those 5, only one of them also involves A. So if we know that event B has occurred and we then ask what's the probability of A given that knowledge, the answer is going to be 1 in 5, which is a different thing from the probability of A when we didn't make that kind of specification. And we might now call this the unrestricted probability of A, the probability of A without making any assumptions about any other events. You might wonder whether a reversal yields the same result. What if we asked what's the probability of B given A? Assuming that event A has occurred, what's the probability of event B? It's actually not the same as the probability of A given B in general, although it could be sort of by special circumstance. If we know that A has occurred, we're limited now to these 6 outcomes. And of those 6 outcomes, only one of them involves event B. So the probability of B given A is 1 out of 6. It wouldn't be too difficult to give a definition of conditional probability, given this discussion that we've had up to this point. We could say the probability of A given B is the usual sort of ratio that we tend to form. But now, instead of the entire sample space being in play, all that's in play are the outcomes that are in B. So if we're defining probability of A given B, then the denominator is the number of outcomes in B. The numerator is the number of outcomes that are in both A and B, and we have notation for that. That's the number in A intersect B. So there's your definition of conditional probability. The probability of A given B is the number of outcomes in both A and B divided by the number of outcomes in B. Now, we could go through and divide both the numerator and the denominator by the number of outcomes in the sample space, and what you end up with is that this is equivalent to the probability of A intersecting B divided by the probability of B. So if you happen to know the probabilities, you can form this fraction. If you happen to know the raw numbers of outcomes, you can form this fraction. They should be equivalent because you're essentially dividing by 1 when you convert this thing into this thing. You can then rewrite this a little bit. If we take the probability of A given B being equal to this fraction over on the far right, we can multiply through by the probability of B, and we can say that the probability of A intersect B is the probability of A given B times the probability of B. And this is a little formula that one sometimes sees that relates these three concepts. We'll do a quick example that involves a contingency table and some conditional probabilities, and it goes like this. Let's suppose we've got a group of 26 students, and of those 26 students, we know that 2 are seniors, and of those 2 seniors, one's male and one's female. We know that there are 10 sophomores altogether. We know that there are 12 males altogether. And we know that 30% of the sophomores are male. And from that, we're going to ask a number of questions about the associated probabilities. And so we'll start by making a contingency table, which is my favorite way of organizing all of this stuff. So we'll have gender identification in one dimension, and for the sake of convenience, we'll assume the binary, although we know that's not always how it is. And then we're going to have some sophomores, some juniors, and some seniors. And let's start filling things in. Where there are 26 students altogether, we know that there are 2 seniors, one of whom is male and one of whom is female. We know that there are 10 sophomores. We know that there are 12 males. And we know that 30% of the sophomores are male. Well, there are 10 sophomores, and 30% of 10 is 3. And now I think we have enough information to fill in the rest. Certainly 7 of the sophomores would be female. And let's see, 3 and something and 1 have to add to 12, so I'm going to say that's 8. And 7 and some, well, let's see, 26 minus 12, this has got to be 14. 7 plus something plus 1 equals 14, so the something's going to have to be 6, and these are going to have to add up to 14, and we can sort of check ourselves down the side here. Is it the case that 10 plus 14 plus 2 equals 26? Yes, it is. When you've got everything organized in a contingency table, it's pretty easy to grab the various probabilities that you might need. Probability somebody is a junior. Well, we've got 14 juniors, and we've got 26 students altogether. Probability someone is a female given that they are a junior. Well, the minute we know somebody's a junior, we're down to these 14 people. And of those 14 people, 6 are female. So we can just sort of pluck our numerators and denominators for this calculation pretty easily out of a contingency table once we have one. Probability that somebody's a junior given that they're a female. Well, let's see, we got 14 females. It's a different 14 from that one. It happens to be the same number. And of those 14 females, how many are juniors? It looks like it's 6. And so this is also 3/7. These are not necessarily going to agree, as we saw a short while ago, but in this case they happen to. And finally, just for kicks, what's the probability somebody's a male given that they're a junior? Well, let's see, we got 14 juniors, of whom 8 are male, so that's going to be 4/7. Here endeth the lesson.